All right, so welcome back, ladies and gentlemen. This is part 2 of the video talking about the intro to rotational kinematics. This particular section is going to focus more on practicing the problems. So, what I would like you to do is we're going to talk about A here, okay? And then I'm going to let you work through B, and then we'll talk about C together. So, for part A, we have a truck, and this whole question is all about, we have a truck that's basically moving forward, and then it slows down, and over a distance of about 100 meters before it finally stops. Now, it has tires that are rolling, which means they're rotating and moving forward while it's doing this. And the tires have a diameter of 80 centimeters. Okay, so the first thing we want to do is I actually want to know the angular velocity. How fast are the wheels spinning before the truck starts to slow down? All right. Now, originally looking at it, there's not really much on this question that tells us much about rotational motion. In fact, if I tried to write my kinematics chart for rotational motion, if I had those omegas, I had the alpha, delta, delta theta, really great drawing there, I know. But I'm not really worried about it because you'll notice I don't know any of these things. Yikes. But that's all right. Because once again, we know that we actually have a relationship between things, linear velocities and angular velocities. All right. And our benefit here is that we know that if this truck is moving at 20 meters per second, that means that the edge of the tire also has to be moving at 20 meters per second. Its linear velocity of the edge of the tire is 20 meters per second. So what that means is that I can look at this and I can say, all right, I know linear velocity and I know something about the radius of the tire. So I can use my relationship between linear velocity, angular velocity, and the radius to actually solve for the angular velocity. All right. And I know before the truck starts decelerating, starts to slow down, its linear velocity is 20 meters per second. All right. I don't know omega, but I know that the radius of this tire is 40 centimeters. So remember, diameter is 80, so the radius is half of that. And of course, I don't want it in centimeters, so it's 0.4 meters. So going through there and using that relationship between linear and angular velocity, you get that the angular velocity is 50 radians per second. All right. And right there, once again, ladies and gentlemen, we're seeing this idea that we can use that linear and angular relationship to find different things that help us out here. Okay. Now, for part B, I want you to solve for the number of revolutions it takes for the wheel to basically, how many revolutions does the wheel go through before it finally stops, or the truck stops? Okay. Now, let me tell you, there's two ways to do this. There's a very short way and a much longer way. Both of them are completely right. But I want you to take the next 4.5, 5 minutes, however it takes, and I want you to pause this video, and I want you to work through and see if you can get the number of revolutions. All right? So pause the video here, work through it, come back. All right, so if you had a chance to work through part B, ladies and gentlemen, there are two different ways to do this. Okay, now on the sheet that I have posted, my key, I did it the long way. And the long way means that what you do is you actually can do two kinematics charts. And what you can do is you can have a linear kinematics chart for the tire moving to the right, and you can also have a rotational kinematics chart for the tire as well when it's turning. Okay, you can do both of them at the same time and it doesn't cause any issues. Now, if you write out your rotational kinematics chart, you actually don't know enough. You only know two things, and that's the starting rotational velocity and the final rotational velocity, which would be 0 because it stopped. You don't know anything else. But what you can do is use linear kinematics to solve for the time it takes for the truck to stop, and then put that time in the other chart, and then you can use it to solve for what you want. And you will get a delta theta, and then you can solve for the revolutions. Just by judging how long it took me to explain that, that's a lot of work. But instead, the other way you can do it is once again using our relationship between a linear value, and a rotational value. All right, and I was really impressed. Multiple people figured this out during the Zoom call, which was awesome because I had not even thought about this. So I really appreciate those of you who figured this out. So the simple way to do this is just think about the fact of what we're told in the question and what we're looking for. If we're looking for the number of revolutions, we know we're solving for delta theta. Okay, that's what we want to eventually get to number of revolutions. Well, in the question, it doesn't tell us anything about delta theta, but it does tell me something about delta x. And what's great about this is that delta x is the distance the tire is going to travel. And what I know as well is that delta x is related to the number of radians I travel times the radius. All right. Now, because of that, I can use this relationship to solve for delta theta easily. Because what I can say is, oh, I know delta x is 100, and I know the radius is going to be 0.4. So I can solve for the number of radians this travels through, which I believe, looking at my notes, is about 250. And then once you have that, if you know delta theta, to count the number of revolutions, it's just delta theta divided by 2 pi. All right? And if we know that, you should get that the number of revolutions is about 39.8. All right? And once again, ladies and gentlemen, that's just a great way for us to kind of see how we can use kinematics multiple different ways, but honestly, the easiest way is to just use the linear and rotational relationships. Okay? Now, the last piece of this has to do with this question about a pebble. And this question can seem kind of strange at first, but this is what it's saying. Let's say I get a pebble stuck in the tire, and I start to drive forward. Well, by the time I stop the truck, linearly speaking, the pebble has traveled, and we'll do it at the very top here, the pebble has traveled from where the truck started to slow down all the way to the end. So it's technically traveled 100 meters. All right? But the other issue is that while that pebble was traveling forward, it was also being spun around on the tire, which means it starts to look, actually, as it's traveling, something like this. Which means the total distance it travels is not just the 100 meters it went from left to right. It also has to include the distance it went around the circle as it was moving, as the whole truck was moving to the right. Okay? Now, that means that the delta x, the total distance this thing travels, is going to be equal to the 100 meters of the first one plus something else. And what we have, and honestly, what we can do is, once again, we can kind of go back and look at this. All right? We can say to ourselves, oh, I know that the truck moved to the right 100 meters, so the pebble must have moved to the right 100 meters. I also know that from what I calculated in part B, I know that the pebble turned 39.8 revolutions. That's the amount of times it went around the circle as it was going that way. What I can do then is to calculate the distance it went around the circle, is I can literally just say, oh, well, the distance is going to be equal to the number of revolutions, because that's just the number of times I went around the circle, times the circumference. Because the circumference is the distance I go around in one revolution. So if I multiply by the total number of revolutions, I should be in business. Remember, circumference is 2 times pi times the radius. The radius here, once again, is 0.4. So if I do that, I get that the total distance this pebble traveled, if I actually measured it, would not be just 100 meters, but it would actually be about 200 meters when all was said and done. All right? And this is something just to kind of make us think about the fact that when things are rotating, they actually travel a farther distance than we realize. All right? So now, that's part 2. Part 3, I want you to work through this one yourself, please. When you're done, you can come back and we'll talk about the answer to this. But the one thing that I do want to talk about for this is just for going between RPM and radians per second. RPM is a measurement of angular velocity. It's the one we're more common with. We see it a lot when you're working with cars, you're working with things that might involve objects spinning. RPM stands for revolutions per minute. Unfortunately, that's not the same unit that we want for angular velocity. So what we do is to go from revolutions to minute to radians per second, we have to start by saying, all right, we have 1800 revolutions every minute. Okay. Well, what we do is to get rid of the revolutions part is we say that 1 revolution is equal to 2 pi. All right. And that way now it's in radians. And the other thing we do is to get rid of the minute, we say 1 minute is equal to 60 seconds. All right. So once you have that, you can calculate the angular velocity before and after. But with that being said, I am confident we have enough notes now. I want you to try and work through A, B, and C, please. All right. So pause the video, go through A, B, and C. When you think you got your answer, come back and we'll talk about it. All right. So, ladies and gentlemen, I apologize. I'm going to talk a little bit faster because I'm slowly running out of time in my recording. For part A, we start with this automobile engine. It's spinning at 800 RPM, and it starts to speed up and increase to 5,000 RPM in 2.4 seconds. Now, question A is asking, what's the angular acceleration of the automobile engine when it's just spinning at 1,800 RPM? And hopefully you thought about this and said, that doesn't make any sense. It's not changing, and that's great. Because this actually kind of is almost a trick question, because what it's asking is this thing having any acceleration if it's spinning at a constant rate? And the answer is it's not. The angular acceleration is 0. Because what's happening is this is spinning at a constant rate, which means it's not accelerating at all. So it's just like linear acceleration. If something isn't speeding up or slowing down in linear motion, its acceleration is 0. If something isn't spinning faster or slower, its angular acceleration is also 0. All right? Now, for part B, we go back to, we can actually use kinematics. All right? So if you convert correctly your RPM, so 1,800 and 5,000, what you should get is that the starting velocity for this is going to be about 188.5 radians per second. So that's going to be the starting velocity. The final velocity should be about 523.4. We know the time is 2.4 seconds. And right there, I know 3 things. I can use it to solve for the fourth, which in this case is I'm looking for alpha, for angular acceleration. All right, so I would use the first equation from the top. If you do that, you should get that the angular acceleration for this is 139.54 radians per second squared. Okay, and right there, once again, we just used our chart. The only thing we had to modify is just we had to do a little bit of manipulation to get from one unit to another. And then for part C, the realm of revolutions, at this point we should know, as soon as we hear that number of revolutions, I'm looking for delta theta. You're solving for it using your chart. You should know, you can pick anything now because you know it. If you solve for delta theta, you'll probably get it's about 854.28 radians. To get the revolutions, just divide that by 2 pi, and you should get that it's about 135.9 revolutions. All right. And once again, just looking at this, ladies and gentlemen, all of these things that we talked about for this question, all of them are related to linear kinematics. Asking an idea about acceleration of something that's got constant velocity. We've done that before. Calculating acceleration if we have a changing velocity. We've done that before. Trying to figure out basically how many times we go around a certain thing. We've done that before. All right. So we're just going back to this idea, ladies and gentlemen, that we have seen this before. We know what's going on. So now, to finish up for the last part. This very last question. The Earth has 2 angular velocities, rotation on its own axis, and revolution around the sun. What that means is that when the Earth is moving, it is actually turning 2 different ways. One of the ways it turns is it is rotating on its axis, so of course that's what gives us the day. The other way is as it's going around the sun, it is going kind of in a rotational motion because it's going in a circle. And I want to know which of the angular velocities is greatest. Okay? And in fact, it both comes down to this. That's not a triangle. Apologize. It goes back down to this relationship. All right. The angular velocity of something is just dependent on delta theta divided by the time. Well, in both cases, what's rather interesting is that whether I'm going around the sun once or I'm turning the Earth once, I still cover the same delta theta, 2 pi, because I'm going around a circle once. But the Earth goes through a day much faster than it does go through a year. So in fact, the amount of time it takes for it to rotate its own axis is much less. So its angular velocity for the day is much higher than the angular velocity of a year. All right. So with that being said, ladies and gentlemen, I am just about out of time. So I hope if you have any questions, come to office hours. Otherwise, have a great rest of the day. I'll talk to you later.